Hey everybody, welcome to lecture 4.3 on limits and continuity of multivariable functions. In this video, we're going to learn about the definition of a limit of a multivariable function and what it means to estimate or even directly calculate the value of a multivariable function as the input values approach a certain xy pair. We're going to use the squeeze theorem, or a version of the squeeze theorem we'll learn today, to evaluate some limits, because in general, these can be more difficult than single variable limits. And finally, we'll learn about the definition of a continuous multivariable function and how to apply that definition in problems. And in general, you'll notice that these are the basic ingredients to set us up for doing calculus on multivariable functions. If you think back to Calc 1, you learned about limits and continuity and ways of evaluating these definitions in different problems before we ever learned about the first derivative of a single variable function. That's the trajectory that we're taking in these videos. And in the next couple sections, we'll learn about how to do calculus to multivariable functions. Let's get started with the definition of a limit of a function of two variables. There's a similar definition in higher dimensions if we have more input variables, but we won't talk about that at all in this class. Already, it's a more complicated definition in theory than the single variable definition of the limit of a function f of x. But on face, the notation looks very similar. And I want to convince you on this slide that the actual ideas behind the limit of a multivariable function are similar and even really the same in principle as a single variable limit. So here's the definition of the limit as xy approaches a, b of f of xy equaling some real number L. So this limit equals L if we can make the values of the function f stay arbitrarily close to L by restricting to a sufficiently small neighborhood of the point A, B in the xy plane. What does this mean officially? Well, there are a few ways to think about this definition and really to study it rigorously. In general, I just want to mention that proving that a limit exists and equals L is much harder than showing that it doesn't exist. And this is sort of the case in single variable calculus as well, although we have lots of formulas and rules that we learned about single variable functions that allowed us to pick these things apart. Here in multivariable land, things will get more complicated. And it turns out to be even more difficult to show that some limit does exist than to prove that it does not exist. Right after this slide, we'll see 3 examples in a row where the limit does not exist. You might not expect that to be the case. For an official rigorous definition of a multivariable limit equaling L, we can turn to the old epsilon delta definition of the limit of a function from single variable calculus. Before I read what it says on this slide, think back to the epsilon delta definition, which you may not remember. It may have been a while. You're not required to use that in this course, but for the sake of rigor, if we choose an accuracy threshold that we usually call epsilon, it's some small positive number, and we want to be within that amount of the target L, which we think is the limit, then in order for L to be the limit, for any threshold epsilon that we pick, we have to be able to choose a value delta so that when we stay within delta of the input limit, as x approaches a, in other words, then the outputs f stay within epsilon of L. Sometimes we call this target practice. If you didn't learn it that way, that's okay. We're not going to talk about it too much here. But how does it work for a two variable function? It's basically the same setup. We just need to tweak what it means to stay within epsilon or delta of something. So first, for any amount of closeness required, that's our target accuracy or our accuracy threshold, epsilon. You should think of this as a small amount of tolerance away from the target L that we're allowed. And epsilon is a small positive number. For L to be the limit, we have to be able to find for any of those epsilons a radius delta, which is a distance away from A comma B that we're allowed to travel by a little bit and stay within epsilon of the target L. So the way this definition reads again is for any epsilon, we have to find some radius delta that's some distance away from A comma B that we can travel. And by choosing XY inputs inside of that circle of radius delta centered at AB, the difference f of xy minus L stays within epsilon, or is less than epsilon. So the outputs stay within epsilon of the target L. Let's do 3 examples as promised that show that this is a more complicated and nuanced definition than it was for single variable functions. So here's a function, x squared minus y squared divided by x squared plus y squared. It's a rational function in two variables. And we're interested in calculating the limit as x and y both approach 0, 0. So notice first and foremost that 0, 0 is not in the domain of this function. If you plug those values in, you'll get undefined or divide by 0. And the problem here is that if we want to, I mean, really, what does it mean to choose a small enough range of values? We're really going to draw circles of some radius delta and shrink the radius down. You can forget about delta now and the epsilon and that whole rigorous definition. What we really want to picture in our heads is inside the domain of this function, which is some subset of the xy plane that I've showed here. We want to draw smaller and smaller circles about the limit value that we're approaching, which is 0, 0. And as we draw smaller and smaller concentric circles, we shrink the radius down. We want to show that inside of each of these circles, the outputs f of xy converge to some value. And that value would be the limit. Well, I'm suggesting that this limit does not exist. So let's think of ways that it could go wrong. And I've already written out one suggestion for this problem. The real problem here is we can approach along different paths. And specifically for the first problem we're doing together, we can approach along the different coordinate axes, the x-axis and the y-axis respectively. We'll actually be able to get different limits. Now this seems weird, but we'll see what comes out as an answer and try to interpret it graphically at the end of the problem. So just taking my word for it, if we want to approach this target of 0, 0 and show that we get different values, why is that going to show that the limit does not exist? Well, notice that no matter how small I draw my green concentric circles, as I shrink their radii down, there are always blue points along the x-axis and red points along the y-axis inside of those smaller and smaller circles. So if the x-axis inputs are converging to a different value than the y-axis inputs are converging to, then there's no possible way for the entire function to converge to a single value within those circles. So I've color-coded everything, blue for the x-axis, red for the y-axis from here on out. So let's work through the following description, and then I'll let you do the other one before I work it through as well. So points on the x-axis are all of the following form. Their coordinates are x, y in general. They're in the xy plane. But if we lie on the x-axis, then we have no height or no y component. So the x coordinate or component is whatever we want it to be, but the y component is 0. So if we approach along this path of approach, the x-axis, either from the left or the right, we're approaching 0, 0, but our points x, y are of the form x, 0. And in that case, well, it's enough to just let the x coordinate go to 0 since y is already at 0. If we plug in y equals 0, we'll get x squared over x squared. And if you cancel those powers out and take the limit, you'll just get 1. So the function heights or the function outputs are approaching 1 if we only approach along that horizontal axis. Let's see what happens for approaching along the y-axis. If you want, this is one you can do. It's exactly the same procedure, but you are supposedly getting a different answer. Pause the video now if you want and try this one out for yourself. Okay, and if you've done that, or if not, let's work out the same approach. So points on the y-axis now, it's the vertical axis. In this case, have no x coordinate, but they have some y coordinate, which we don't know what it is. We'll just leave it at 0, y. Which means if we approach 0, 0, and all of our points are of the form 0, y, well, it's enough to let the y coordinate go to 0 because the x coordinate's already equal to 0. And if I plug in x equals 0, I'll get negative y squared over y squared, which reduces to -1. Take the limit, you get -1. So we saw that approaching from 2 different directions or along 2 different paths gave us 2 different limits. You can think of this like an oscillating function. You remember the sine and cosine functions tend not to have limits at infinity. You can arrange for things like sine of 1 over x, for example, won't have a limit as x approaches 0 for reasons of oscillation as well. And you can think of this as sort of a 2-dimensional version of the oscillating problem, where inside of any small circle I draw around the origin, I have points that have height 1 and points that I have height -1. And I can swing around my input point inside that circle and get plus and minus 1s all over the place, along the different axes in particular. So I can't actually converge to a single height, because I always have outputs that are far from each other. let's go right into the next example and think about another type of function that apparently does not have a limit at the origin. So in this case, xy over x squared plus y squared, again, does not have the origin in its domain. And if you check, and I encourage you to pause the video and do this in a moment, if you check using the same approach as the last problem along the coordinate axes, where we have points on the x or y axis, and we approach 0, 0 that way, you'll see that actually both functions, or the function has a limit along both of those paths of approach. However, that doesn't mean that there's not some other way to force different values to come out of the limit. And in particular, as suggested by my picture, we could approach along different lines that pass through the origin. For example, the two lines y equals x in blue and y equals negative x in red. Let's see what happens in these cases. So points on the blue line y equals x are all of the form x comma x. So the x coordinate is determined and y is just equal to x. So we can take the limit just as that x coordinate goes to 0, since they're the same, of, now if I'm going to substitute in y equals x and reduce things, I'll get x squared over x squared plus x squared. The denominator is 2x squared, and I can cancel out powers of x, and I'll get a limit of 1/2. Okay, and if you worked out either of the coordinate axes in this case, you might have already seen, oh, this limit doesn't exist. This seems to be an issue with taking a limit as we approach the origin from different directions. But I'll work out the other, the red line that we wrote down, which was y equals negative x. So the coordinates look like x comma negative x. This limit is the same as the limit if we just let the x coordinate go to 0 of the expression. So now x times negative x, that's negative x squared, over x squared plus negative x quantity squared. And the trick in the denominator, you can see, is that you'll get x squared plus x squared, or 2x squared again. Cancel the powers of x, you'll take the limit and get negative 1/2. So approaching along these two different directions or paths gave you a limit of 1/2 or negative 1/2. And you can think of this, and there's no sine or cosine in sight, but you can think of this like we're oscillating between these two heights, plus 1/2 and negative 1/2, inside of smaller and smaller circles around the origin. We can't ever decide what's the true target, so we'll say that the limit does not exist. But it can be worse than that, so let's do one more example together. Here's a function that we, again, see does not have the origin in its domain. It's xy squared divided by x squared plus y to the 4th. And things are worse, or maybe better if you like this sort of thing, if it's kind of an interesting problem, computing multivariable limits. In any case, what gets more complicated here is you can check that the limit, not just through the axes, not just through y equals x and y equals negative x, but actually through any line y equals mx that passes through the origin, exists, and they all equal 0. So if we take a straight line path, a straight line of approach towards the origin from any direction, and you can even check, so y equals mx only gives the non-vertical lines, but you can use the y-axis as a direction of approach as well. You'll see that they all have the same limit. But as the problem title suggests, yet another limit that does not exist. There's something else going on. And if you think about it, if we're trying to stay within a certain target value on circles centered at the origin or within those smaller and smaller circles, we could approach along different paths that also give you points inside of all of those concentric circles, but maybe are not straight lines. And you might not come up with this on your own for this problem, but I'll just give it to you. A path that's going to present problems for us is the rightward facing parabola x equals y squared. So again, let's draw some concentric circles. I'll just draw 2 of them. The claim is that as we shrink down the radius of these circles, we'll have infinitely many points along lines like y equals mx that we know approach 0, but the claim is that these infinitely many points on the red curve, x equals y squared, will converge to a different output value of the function. And therefore, we will be able to oscillate or move between different heights within any sized circle around the origin. So let's work this one out together. So it's a little more complicated. Here, our points look like, well, whatever the y coordinate is, x is equal to y squared. So we have coordinates that look like y squared comma y. So it's enough to take that y coordinate and shrink it to 0, because then the x coordinate goes to 0 as well. Excuse me. And if we if we evaluate, if we substitute in x equals y squared, we'll get y to the fourth in the numerator. Let's see, x equals y squared, that'd be y to the fourth plus y to the fourth. And here we can cancel things out. We'll get positive 1/2. And we didn't actually check together what the lines would give you, but hopefully you trust me that the limit equals 0 along those lines. And if you don't trust me, this is a good thing to pause and check now, or you can check this at the end of the video. I really encourage you to check some other lines. And you can actually do it for any line that's not vertical all at once using the equation y equals mx, and m will be some number. It'll turn out to give you an answer of 0, which is different than this answer of 1/2. If you wanted a different curve that's not a line, well, I'm not going to give this away, but there's a way to check along other curves as well. Really, you can check any curve that intersects the origin at this point using the same technique. So those are 3 limits that do not exist. And somehow these rational functions are really the culprit. When we have numerator and denominator with powers of x and y, things can often go wrong in the multivariable world. By the way, here are 3 graphs of those functions. You can see that in straight line approaches, here along the axes, you can see the +1 and -1 pop out. And this isn't drawn very clearly in this computer graphic, but there's really a vertical asymptote at the origin in this function that can't be patched or replaced by a piecewise definition. Likewise, for our second example, the issue here was really the lines, not the axes, but the lines like y equals x, which is shown here, or y equals -x, which isn't shaded, but you can see it's below the axis at height -1/2. And finally, even though all of our straight lines may converge to 0, or the limit values go to 0 along those, this parabola somehow sticks out above the xy plane and gives us positive heights of 1/2 that we saw. So functions can do weird things in multiple variables. That's sort of the punchline here. What sort of tools do we have to evaluate things? Well, this slide is pretty much all the tools we're going to develop in this course. There are lots and lots of rules we can use even from single variable calculus, such as if we pick a path and we're able to express our points x comma y as something like x comma x squared, or we just did y squared comma y, then we're just really evaluating single variable limits. So the notion of taking different paths of approach is actually a useful one because it reduces the problem to a single variable limit. Beyond that, we actually have all of the same basic algebraic operations from single variable calculus that we can use, such as the sum and difference rule. If I have 2 multivariable limits that exist and I add those functions together or subtract them, then we just add the limits or subtract the limits to get the answer. Likewise, multiplying by a constant number, or multiplying 2 functions, or taking a quotient of 2 functions, as long as denominators are not equal to 0 or going to 0, all of these things will behave correctly. I didn't write these out, but you can see what they say in the book. Finally, the squeeze theorem. We're not going to talk a ton about this, but it's basically the same form as every squeeze theorem you've seen before, with one small caveat. But the squeeze theorem says that if we have our function f we're interested in computing a limit of, squished between or squeezed between some g and some h, 2 other multivariable functions, then as long as the limit of the outer functions g and h converge or exist in equal sum L, then f has to have the same limit. And the key change here is we have to say if this inequality or this pair of inequalities holds in some neighborhood of our point AB, which again means in some small circle of AB, if we have this relation between the 3 functions and the outer functions go to the same limit, then so does the inner function f. So that's the squeeze theorem, and this can be useful in many circumstances. Finally, let's wrap things up by talking about continuity, because this will be our main concept going forward to start studying continuous multivariable functions, followed by differentiable, and so on and so forth. So a function is continuous, and this is actually an identical definition to the single variable definition. So function f of x comma y is continuous at a point a comma b in its domain if the limit as xy approaches ab of f of xy equals the function value f of ab. You may remember a 3-part definition of continuity from Calc 1. It's all wrapped up into this single equation. You'll see that, first of all, ab is in the domain of the function. That's what it means to even be able to write this value as a real number. Second, this limit has to exist. That's why we're even able to write the limit as a real number. And third, these two real numbers that we just said exist have to equal each other. So this is shorthand for the three-part definition, but it's exactly the same as it was in Calc 1, except again, now we have limits of multivariable functions, which are a little more sensitive, needing circles of shrinking radii to prove. Here's a quick theorem that will allow you to do most problems where the limit does exist in this class. Polynomials, root functions such as square root, cubic root, etc., trig functions, exponential functions, and logarithms, ln of blank, are all continuous on their domains. So as long as you can evaluate what the domains of those functions are, then all of these functions are continuous, and to evaluate a limit, you can directly plug in the target a, b into the function. And that's the same as it was in single variable calculus. Oftentimes we don't even think about computing a limit when we compute the limit, right? Secondly, sums, differences, products, quotients, and compositions of continuous functions are all continuous on their domain. That's a lot to unpack, but the first four are basically based on that limit property we just worked out. If I take the sum, difference, product, or quotient of two functions and their limits exist, namely their limits exist at a comma b, then we can add, subtract, multiply, or divide those limits in order to compute the limit of f of xy combined with g of xy in that same way. These are really important to write out the first few times you're doing these things, just to remind yourself that they work, but they work and we can use these going forward. Composition, by the way, is just saying if I take f of x comma y and g of x comma y and stick each of those into the two components of some other function h, basically take the outputs and throw them back into another two variable function, h of f comma g, in other words, composing multivariable functions, then those are, as long as everything's continuous in each piece, the whole expression is continuous. By the way, each of our examples where the limit did not exist and then the function was not continuous at that value was an issue because it was a quotient of polynomials, also called a rational function. But in particular, 0, 0 wasn't even in the domain. If we had added a value at 0, 0, we actually showed that there was no way to write a piecewise extension of those functions f of x comma y and get a single value for the limit so that we can line it up with f of a comma b, or f of 0, 0 in that case. So those were very strongly discontinuous functions, and discontinuous is the same terminology as we've had before. Okay, cool. So that's basically all I want to talk about in this video. We're going to get to do some calculus next time. But as some closing remarks, limits, continuity, and all of the theorems that we've learned can also be extrapolated to functions of higher dimension or functions of more than two variables. As we saw at the end of each of the videos for chapter 4 so far, there's an easy way to extend all of the notions we've discussed to higher dimensions. The only trick to doing any of the things in this video for 4.3 is to make sense of those shrinking radius circles concentric about the point that we're interested in evaluating at. And what will happen in higher dimensions is we'll say that that delta value, which we're treating as a radius now, will be a distance of any point away from that target point. We can have as many coordinates to the target points as we want, and the functions will take that number of variables in as input and spit out a single number. And as long as our output values converge to a single value, as we shrink our distances away from that input number, the input coordinates down to 0, then we'll say that the limit exists. Likewise, continuity is that the limit equals the function value at that point. All of the theorems will apply as well. Here are a couple summary questions to think about. Why is it harder to verify a limit of a multivariable function? And next, what do you need to check in order to determine whether a function is continuous or not as a multivariable function? That's it for this video. Thanks for tuning in, and I hope you're excited to start computing derivatives of multivariable functions, whatever that means, next time.